Okay. Before we start going over the worksheet, I have a couple comments on the homework. I did receive emails from many of you. Email was the way to submit the homework. I've not sent feedback yet. I plan to send feedback to everybody by tomorrow afternoon, maybe evening. I did start grading. I graded some of them, but I like sending feedback all at the same time. So I believe I will have feedback sent by tomorrow afternoon. It'll be in a reply to your email. So any questions about the homework? Okay. Any questions about the material before or for this week before we start the worksheet? Okay, so let's get into this worksheet. This week we talked about limits as x goes to infinity, as x goes to negative infinity, and vertical and horizontal asymptotes. And we talked about continuity. Well, let's start this worksheet. First one, we have a limit as x goes to infinity of this function, a rational function, polynomials on top and the bottom. And the way we will handle a limit like this is by observing the largest exponent on the bottom, which is 9. That exponent is 9, and what we'll do is multiply our function that we have by 1 in the form of 1 over x to the 9th over x to the 9th. And this will allow for a convenient simplification. So that limit now equals this limit of what? Well, let's see, 5x to the 5th over x to the 9th as side work. Well, the 5 is still there, but notice we have 5 x's here, we have 9 x's here. So 5 on the top and the bottom will cancel, and you're left with 4 x's in the bottom. So distributing 1 over x to the 9th into the first thing gives us 5 over x to the 4th. And similarly, for this one, the 4 will stay. X cubed over x to the 9th, 3 x's will cancel, so you're left with 6 x's in the bottom. And negative 1 over x to the 9th. There's no simplification with that. And now we do the same in the denominator, but here notice x to the 9th over x to the 9th is just 1. Negative 3 x squared. Yes. Can you repeat that? Okay, I didn't hear that question a second time. Okay. Maybe it was resolved. So here we have negative 3x squared over x to the 9th. The negative 3 stays. X squared over x to the 9th, 2 x's cancel, so you're left with 7 x's in the bottom. And now, with this limit, we can push this limit into each piece and take the limit of each piece. Where should I write? Let's write it over here. As x goes to infinity, 5 over x to the 4th will go to 0, because this denominator here, as x gets larger, this denominator is also getting larger. So 5 divided by larger and larger things will keep getting smaller and smaller and approach 0. And similarly, this limit would be 0. 4 divided into larger and larger numbers, or by larger and larger numbers, will keep getting smaller. And similarly, this one will approach 0. This approaches 0, I mean, from the negative side of 0, but it still approaches 0. And in the denominator, as x goes to infinity, 1 doesn't change. And 3 over x to the 7th again goes to 0 as x goes to infinity. And then this fraction is 0 over 1, which is a fraction which reduces to 0. So observe the denominator and multiply, and then it'll turn into something like this, where you can then take limits on each piece. Any questions about this one? Okay, this is 1a. I'm going to, after we do 3a, I'm going to reference this problem again. So we'll keep this in mind. So any questions about this one? So next we have 1b. A little different toward the end, but at the beginning it'll look the same as this one. So what do we have? 4x to the 8 minus 1 over x to the 4 minus x squared. So here again, limit as x goes to infinity of a rational function. We'll look at the largest exponent on the bottom. So with these, we are, well, I am looking at the largest exponent on the bottom. There is a parallel way to cover these using the largest exponent on the top. It's very similar, except like 0 and infinity kind of get flipped around. But I will always look at the largest exponent on the bottom for these. And they'll all work out generally in the same way, the same type of way. But you could, if you want, see what happens when you do an argument looking at the numerator. But I'll do the denominator. Here, denominator's largest exponent is 4. So we'll multiply everything by 1 over x to the 4. And what do we get? Well, that limit now equals this limit. 4x to the 8th over x to the 4. Well, what is that? Well, the 4 stays there. But we have 8 x's up here and 4 x's down there. So 4 of them are going to cancel. And we're left with 4 x's in our numerator. Next, negative 1 over x to the 4th is just negative 1 over x to the 4th. That doesn't reduce. And in the bottom, x to the 4th over x to the 4th is 1. And negative x squared over x to the 4th, 2 x's will cancel. So we get negative 1 over x squared. Now, to do this limit, I'm going to do it in 2 steps, actually. I'm going to first notice as x goes to infinity, this term up here and this term down here will go to 0 as x goes to infinity. This term over here goes to 1 as x goes to infinity. It doesn't change. So I'm going to make that observation, which allows this to simplify. How? It allows it to simplify to this. 4x to the 4th, it'd be 4x to the 4th minus 0 over 1 minus 0. So 4x to the 4th over 1, which is just 4x to the 4th. Now, to handle this limit, well, there are a few ways you could approach it. I usually like to approach this with an observation of the graph y equals x. Because for y equals x, or for FOR, the equation y equals x, the graph of y equals x, we can use the graph to observe that the limit as x goes to infinity, this function is also going to go off to infinity. So as x goes to infinity, x goes to infinity. It's kind of an identity relation. But we can use this to compute that limit. As x goes to infinity, well, we can use the algebraic limit laws, which tell us we can multiply this by a 4, and we can raise it to the 4th. Well, I should say we could raise it to the 4th and then multiply it by 4, and we're still going to get an infinity, because a finite number like 4 is not going to affect infinity. It'll still, since infinity is a limit which gets larger than anything, multiplying that by 4 will not cause that to not be a limit, which gets above everything. So it will get above everything, which is how we define infinity. Another way, without a graph, to make that observation is you can pull out the 4 and then just deal with x to the 4th, or you could consider this entire function, 4x to the 4th. What does that do as x gets larger? Well, as x gets larger, x to the fourth is going to keep getting larger. And multiplying that by 4 will cause it to continue to keep getting larger. Either way, this limit would be a positive infinity. Either way you want to reach that conclusion, by making this observation and applying some algebraic limit laws, or by looking at this equation and saying, well, as x gets larger, that gets larger, so multiplying it by 4 also gets larger. Any questions about this one? Okay. So I mentioned I would go back to 1a after doing 3a. I will also go back to 1b and make an observation on 1b after we go over 3a. So we'll keep this one in mind. Okay, 1c is next. Limit x to 0, e to x cubed minus x. Now, how would we do this limit? Well, e is an exponential function. The algebraic limit laws do not apply to an exponential function. But what can we do with this? Well, at the end of lecture it's week 3. At the end of lecture 3.2, we discussed a theorem which covers limits of the composition of functions where the outside function is continuous, meaning here, e to the x itself is a continuous function. And because it is continuous, we can compute this limit by doing this. By, I'll write it here, last theorem in lecture 3.2. Right at the end, we discussed a theorem on taking the limit of a composition of functions, a composition of continuous functions. And here, that allows us to compute this limit by pushing the limit into the exponent. Because now, once the limit's in the exponent, we can take that limit by using the algebraic limit laws. Oh, what am I doing? Limit without that doesn't make sense. That's just as x goes to 0. So we can take this limit using the limit laws. We get 0 minus 0, e to the 0 minus 0, which is e to the 0, which is 1. So in well, I guess I shouldn't say it another way. Yeah, I'll just leave it. I already wrote it. So you could answer a question like this, like that. Another way that you could potentially write your answer is like this. I get the feeling there will be one of these more people prefer than others. So that last theorem we covered in the continuity lecture, in essence, allows us to treat a limit like this using a direct substitution. So here we have e to the x cubed minus x as x goes to 0. Well, that theorem tells us we can push the limit there, but what it allows us to do is treat this as a substitution. So right here, jumping from here to here, we did just apply a substitution argument. It is useful to know, especially for those of you who are math majors, if there are any of you. Usually in my calc classes, I get like 1 or 2 out of 50 students being math majors. It is useful for math majors to keep in mind why we can compute this limit. And it is useful to know we can't go from here to here without a result on continuous functions. I mean, the functions we're going to be dealing with, the limits we're going to be taking on them, will be all continuous functions, or at least functions which are continuous where it matters. So if you want to explain why we could take the limit, your work on a test or a homework, you're certainly welcome to. If you don't want to, you are also certainly welcome to. But mathematically, this equals sign is not necessarily immediate. But I mean, this is not a 400 level math class. This is Calc 1. So, I would consider that equals. I would consider justifying this equals sign a far more advanced thing than it seems. So either way you would like to answer a question like this is okay with me. Any questions on this one? So that theorem allows us to treat something like this as a direct substitution.
I have a question about limits in general.
Yes.
When can you stop writing like limit of x as x approaches something?
You can stop writing it once you take the limit. So for what we're doing, once we do a substitution. So here, I stopped writing it once we did a substitution. For the ones with infinity, it's the same thing. You can get rid of them, and we're not doing a substitution with infinity, although in the back of your mind you are allowed to think of it like that. But the limit went away once we took all of the limits. So you'll notice in the work for 1b, right at the end, I still had limit as x goes to infinity of 4x to the 4th, even though I took the limits on all the other pieces. So we can get rid of the limits once we take all of the limits, once we apply all of the substitutions. That's a good question. I was gonna, after I send homework feedback, I usually send an email, like a general email saying, having general comments on the homework, and that was definitely going to be one of them, because it always is after the first homework. Any other questions about this one? Or questions in general? And I forget if I mentioned this, I am going to post solutions to the homework tomorrow. And in that you can see when I stop writing limits. It's once we do the substitution. Part D, limit x to 0 from the right of log x. How can we do this? Well, log is a continuous function, so we can consider this as a substitution, and we get log of 0. But log of 0 doesn't simplify to anything. Log isn't even defined at 0. That's nothing. But how else can we do this limit? I don't see a way to use squeeze theorem, especially because we're getting infinities as our answer. So if we can't do limit laws and we can't do a squeeze theorem argument, well, all we have left is a graph. Unfortunately, we know the graph of logarithm. The graph of the logarithm looks like that. It goes through what is that? 1, 0. Goes up like that, goes down like that. So we have this graph of log x, and we can observe in this the behavior as x approaches 0 from the right of 0. As x approaches 0, well, we're looking at, as x approaches 0 from the right only, it's not defined to the left of 0. We're looking That's supposed to be blue. We're looking at those x values. We're looking at what this function does for these x values. Well, what does the function do? It does this. Keeps going down, and it'll keep going down. It goes down without bound, meaning it gets less than all negative numbers, less than all numbers. And when that happens, we say the limit is negative infinity. This function goes down, limit is negative infinity as x approaches 0 from the right. Any questions about this one? Any questions about anything from number 1? Number 2, we have this rational function. Limit x, oh, no, we don't have limit, we just have the function. We have limits in parts b and c. So we have f of x equals what? X minus 5, x plus 1 cubed, x plus 3, x plus 4 to the 4. Oh, my marker's running out, that's great. Maybe this other one works. Okay, that looks a little better. And in the bottom, we have x minus 3 squared. We have x plus 2 cubed. Oh, no, to the 5th. The other one's cubed. Wouldn't have made a difference if I said it was cubed versus the 5th. And x plus 5 cubed. So part A says find the vertical asymptotes of this function. Well, a vertical asymptote will occur wherever the denominator is 0. So we need to find where the denominator equals 0. Well, conveniently, the denominator is factored nicely for us. You know, I wouldn't give you a degree 10 and expect you to factor it. I wouldn't do that. So set the bottom equal to 0. This times this times this equals 0. Well, the only way things can be multiplied together and get 0 is if one of them is 0. So denominator equals 0. That could equal 0. If x minus 3 equals 0, then x must equal 3. If x plus 2 equals 0, then x must equal negative 2. If x plus 5 equals 0, then x must equal negative 5. So here we have our vertical asymptotes are vertical lines. Here we have 3 vertical asymptotes. I'm not sure if that microphone picked up a noise. There was a very strange noise going on outside my office. Any questions about part A? Okay. Part B, find this limit. Limit as x approaches negative 2 from the right. Well, in part A, we already noticed that this function had a vertical asymptote at x equals negative 2. So from that, we know that the function close to negative 2 is going to look, and it could look like that, where on the one side of negative 2, it goes up to infinity. On the other side of negative 2, it goes down to negative infinity. Or it could look, and they could both go to infinity. Or this could be flipped around. Or they could go to negative infinity. But this part B and C are just asking which infinity are we going to get on each side of negative 2? A question like this tells us some nice information about the graph of that function.
Why did you choose negative 2?
I chose negative 2 because there was an x plus 2 in the bottom. I could have also chosen 3 or negative 5 for this question. You know, I chose, I mean, if it said find limit as x goes to like 6 or something, that would just be a substitution here. But here, we're specifically looking at the behavior close to a vertical asymptote. So because we know there's a vertical asymptote here, oh, was the question, why did I write -2? The question says -2.
No, yeah, it was out of those three values why you chose x equals -2, but
Oh.
now I realize because that's what you're
Okay.
asking for.
Yeah, okay.
Thank you.
Now, the actual reason I chose -2 is because the sign observations we're going to make in B and C are a little less convenient than if I chose the other two numbers. I would say they're less convenient because of this term up here. But we'll see. So on both sides of -2, we know that the limit is going to, on each side of -2, I should say, we know the limit will be an infinity, meaning it'll be a positive infinity or a negative infinity. And all we have to do is figure out the sign of the infinity. And I like to do that using a notation like this. I've never seen this notation in a textbook anywhere, but I like it because I think it points out what's important here. So we have this fraction, this rational function. It's all factored nicely. Everything's multiplied together. So what we're going to do is look at the right of -2 here. I'll just draw that with a number line up here. So we're looking at the right. Oh, I forgot to mention that this morning. Okay. We're looking at the right of -2. So we're looking at numbers over here. And we're going to see what happens for these numbers, what happens to each piece of this. And all that matters is the sign, the positive or negative. So take numbers to the right of -2, but close to -2, substitute them here for x minus 5. Well, that's still going to be a negative. Negative numbers here, -5, are still negative. So we have a negative. Next, numbers close to -2, but on the right of -2, into x plus 1. Well, numbers here, plus 1, are going to wind up like there. In particular, they're going to still not be on the other side of 0 if you're close enough to -2. So substitute numbers on the right of -2 in here. You get a negative number, and you cube a negative number. Negatives cubed are negative. Any questions about that second negative sign?
Hey, you said negative cubed are negative. Is
Yes.
that correct?
Yes. So here, so I'm actually doing two things to get that negative. First, I'm just looking at, so I'm looking at the entire term x plus 1 cubed. So first I'm looking at x plus 1. If we take numbers here on the right of -2 and add 1 to them, they'll still be negatives. And then we are cubing them, and negative cubed is negative. So a negative number times negative number is positive, but then times another negative makes it negative. So any other questions about that second one? I think that's the hardest one of all 7 of these pieces. Okay. So numbers to the right of -2 into x plus 3. So numbers to the right of -2 plus 3, well, that's going to get to the other side of 0, making a positive. Numbers to the, well, this next term is raised to the 4th power, so it doesn't even matter what sign we get on the inside. Anything to the 4th is positive. In this case, we have positive to the 4th, but negatives to the 4th are still positive. So on the numerator, we have those 4 signs. And what do we get on the denominator? Well, here we have something squared. So that's immediately positive. In this case, it would be a negative squared, but negative squared is still positive. Now in this next piece, x plus 2 all to the fifth. Well, what happens if we take numbers on the right of -2 and add 2? Well, if we add 2 to these, they're going to go on that side of 0. Take these numbers, add 2. They go on that side of 0, the positive side of 0. And positives to the fifth are positive. And for this last piece, take these numbers, add 5, they'll become very positive, and cube that, positive cubed is positive. And now here, we just have to count our negative signs. Negative times negative is positive. And then all the other positives are positive. So on this side of 2, on the right of, or on this side of -2, we have a limit of positive infinity. Any questions about part B? Okay. I may have mentioned in lecture, I draw my infinities with 2 circles. You could draw it as like a sideways 8, but I find the 2 circles easier to draw. So for part C, we're looking at the other side of -2, and again, for the same reason as part B, we know it's going to be an infinity. We just have to figure out positive or negative. So in this case, we're looking at numbers on the left of -2. So numbers, farther away from 0 than -2. And again, we're looking at each piece here. Numbers to the left of -2, -5, well, that's just going to get more negative. So that's negative. Numbers to the left of -2 plus 1, well, you add 1 back here, you're still going to be negative. And numbers smaller than -2 plus 1 are going to be smaller than -1. So again, we get a negative and we cube that, which is a negative. Numbers to the left of -2 plus 3. Well, if you add 3 here, and -3 is all the way over there. You move this over 3 units, that's going on the other side of 0. Which makes that a positive. That has an even exponent, so that's always positive. That, again, has an even exponent, so that's always positive. The next piece, x plus 2 to the fifth, well, we're taking numbers over here. Numbers over here. On the left of -2, we're moving them over 2 units. What's that going to do? It's going to put them there. It's going to put them still on the left of 0. So inside here, we have a negative. Raise that to the fifth. Negative to the fifth is a negative. And for the last one, numbers on the left of 2 plus 5 units, so that's going to go way over on the other side of 0, so that's positive. Well, and those numbers to the third are positive. And here we have 3 negative signs, so multiply all them together. On that side of 2, you get a negative infinity. Any questions on, well, before any questions, just observe these 2 pieces, or well, those 2, I don't want to say fractions, but observe the middle step for each of these. And you'll notice the only difference in these signs is down here at this x plus 2 term. And that is how these will work out. These will work out so that the only difference on both sides, well, they will work out so that what happens on both sides of 2 is largely determined by that term. but still, I mean, there could be, a bunch of other negative signs to deal with, but the real difference here will occur here. Meaning if that's an even exponent, then you're going to get the same thing happening here. So you'll get the same thing happening for the ultimate limits. Any questions about this one? Okay.
Mr.
Yes.
Cameron. So
Yes.
for like the function at the top, for the first parentheses when it says it's a negative, how did you get the first parentheses? Like how do you know it was negative?
So this one?
Yeah.
So the first term up in the numerator was x minus 5. And what we're doing for, well, for this first one, we were looking at what happens on the right of -2 when we take these numbers and substitute them in for x minus 5, well, into x minus 5. So if you take a number on the right of -2, numbers kind of, I mean, I always hesitate to write this, but you can think in your mind numbers kind of like a -1.9 type number on the right of -2. You substitute that up here, well, that's going to be -1.9 type number minus 5, and that's still going to be a negative. And similarly down here, instead of considering a -1.9 type number, you can think of a -2.1 type number, substitute into x minus 5, and that would be, it'd be like -7 something. But we're looking close to -2 and on both sides of -2.
What if the let's say the number you plugged in was like 5 and then equal to 0? Like how do you decide if it's negative or positive? So for the thing for the expression up there where it's like x minus 5, what if the x was 5 and then it would equal out 0? So how do you find out if it's positive or negative?
That's a very good question. That
Because with this method, like I imagine that you put in like something that equals 0 and then I'm like, oh, I don't know how to find it.
Yeah. So in all of my explanations, I'm saying we're getting very close to -2. So we're not looking at all numbers to the right or to the left of negative. We're just looking really close to -2. Now, the reason for that gets into the true definition of limit. So the definition we cover in Calc 1, the definition of the limit, is not the true definition of the limit. The true definition of the limit is an optional topic, and usually at the end of the semester, if I have time, I cover it. But it's contained in section 2.5 of our textbook. Now, why does that matter? Well, it matters because in the true definition of the limit, it tells us if we're looking at what happens at -2, it doesn't matter what happens far away from -2. All that matters is what happens really, really close to -2. So when you're doing these, I always use whole numbers in these types of questions. So when you're doing these, always think really close to the number in question. At the end of the semester, I may, depending on the time, go back and talk about section 2.5. But for now, I did skip it because it is optional and I'd rather treat limits more algebraically. That's one possible answer to your question. I'll try, let's do this limit. I think we should have enough time for this. So limit as x approaches 5 from the right. Okay, let's say we have this limit. I'm going to center x plus 2 up here. Let's say we have this limit. So x plus 2 over x minus 5 times x minus 5.0001. What would this be? Well, I will tell you what would it be. This is negative infinity. Now, why is it negative infinity? Well, you do a substitution, you get number over 0. So that does tell you it will be an infinity. Which infinity? Well, let's do our sign argument. We're looking on the right here of positive 5. Now, when I was going over, what problem was that? 2b, toward the beginning, I said, I forgot to mention this in my morning class. It actually was something like this. So I am glad that this was brought up. But what are we looking at for this limit? We're looking at the right of negative 5. The right of negative 5. We're looking over here. Well, okay. What happens when we take those numbers, add 2? Well, that's a positive. What happens when we take those numbers, subtract 5? That's still a positive. What happens when we take those numbers, subtract 5.0001? That's a negative. Why is it a negative? Well, magnify the number line. The limit tells us all that matters. The definition of limit we cover does give what's important in words. It says as values get close to, in this case, 5. Magnify the number line. You magnify the number line, there's a gap between 5 and 5.0001. And we're not concerned with what happens far away from 5. For the limit, we're concerned only with what happens close to 5. And close to 5, you take these numbers, subtract 5.0001. Well, they're going on the other side of 0. So that's negative, which makes it negative infinity. I hope that answered your question and didn't make it more confusing, but that is the actual answer. The actual answer is I would rather spend more time computing things than doing the theoretical definition of the limit, at least for a Calc 1 class. This is a good example to keep in mind. I'm not going to ask one where I just throw a decimal like that, but any questions about this? So when you're doing these, think close to the number in question. You don't have to write this unless you want to. If you want the true definition of limit, there it is. Limit of f of x as x approaches a is L if and only if for every epsilon, Greek letter epsilon greater than 0, there exists a delta, Greek letter lowercase delta greater than 0, such that the distance between the function and the limit less than epsilon whenever the distance between x and a is less than delta. What this really means is if you look close to the limit in question, you can get, in a sense, even closer to this point. So if you take a math class called real analysis, which is generally it's generally one of maybe the 2 or 3 more advanced undergraduate classes you could take. This is like day 1 of new stuff. Well, no, this is technically not new. This is prerequisite for that class. So I prefer to treat the limit algebraically and graphically. Don't worry about that. It is a very good question. Oh wait, I don't need a limit for number 3. Yeah. Number 3, find vertical, horizontal asymptotes for each function. We need horizontal asymptotes, we need vertical asymptotes. Well, vertical asymptotes, let's do those first. Those are generally nicer computation. For the vertical asymptotes, we need to set the denominator equal to 0, so let's do that. Well, how can we deal with this? Well, conveniently, all 3 of these have an x in them. So we can pull an x out. And once we pull an x out, now we have a degree 2 polynomial, which does factor. Because -4 and +2 multiplied together make an 8, added together make, or multiplied together make a -8, added together make a -2. And now 3 things multiplied equals 0. So one of them has to equal 0, which gives our vertical asymptotes. I don't need an and, I guess I'll just square them all. So x equals 0, x equals 4, and x equals -2 are our vertical asymptotes. Any questions about vertical asymptotes for this one? Okay. Now, horizontal asymptotes, remember, a horizontal asymptote can occur as x goes to positive infinity or as x goes to negative infinity. So let's first do the limit as x goes to positive infinity. So we have limit of this rational function, this fraction of polynomials. So we'll handle this by multiplying everything by 1 over x to the largest exponent on the bottom, which is 3. Multiply everything by 1 over x cubed, what do we get? 3 over x cubed minus 2 over x squared. 4x cubed over x cubed is just 4, so -4 over x cubed over x cubed is -4. And what do we get in the denominator? X cubed over itself is 1. -2x squared over x cubed, -2 over x. -8x over x cubed, -8 over x squared. And now we take this limit. That goes to 0. that goes to 0, that goes to -4, that goes to 1, that goes to 0, that goes to 0. So what do we get? 0 minus 0 minus 4, 1 minus 0 minus 0, and that reduces to -4. And in this step, I did remove the limit because we took the limit. Before that, we had not taken a limit yet. We just did some simplification. Any questions about this limit? Okay, now this tells us y equals -4 is a horizontal asymptote, but we also have to take the limit as x goes to -infinity. So let's do that. So in lecture, I described a way to do that. And before mentioning that, I will tell you for many functions, this one included, the work as x goes to positive infinity and x goes to the work we did for the limit as x goes to positive infinity applies as well to the limit as x goes to -infinity. So in other words, one way to answer, which I did not cover in lecture, one way to answer the next limit is using identical work with this type of simplification. And that's because, and that works because, if you look at the function y equals 1 over x, as x goes to positive infinity, this is going down to 0. As x goes to -infinity, this is also going to 0. It's going up to 0, but it's still going to 0. So you are certainly welcome to do an argument like this for this one. Now, why did I cover it in a different way in lecture? Well, I'll get there in a moment. Any questions about this? We're not done with number 3 yet, but any questions about anything we've done for number 3 so far? Okay. So the way we covered in lecture, the way to compute this limit in lecture is to convert it into a limit as x goes to positive infinity by applying a graph transformation, the graph transformation that trades all negative x's for positive x's. So let's do that. So way 2, you could answer limit as x goes to -infinity for this one. Would look like this. Turn into a limit as x goes to positive infinity. Replace all x's with -x. Replace all x's with -x. This -2x would then become -2 times -x, which is positive 2x. -x all cubed is -x cubed, times a -4 becomes a positive 4x cubed. And similarly down here, notice this term, -2x squared, does remain the same because -x all squared is just positive x squared. And from here, we have the limit as x goes to infinity. Largest degree on the bottom is 3, multiplied by 1 over x cubed. And then take the limit as we did before, except with this other function. Distribute the 1 over x cubed in, 3 over x cubed, 2 over x squared, plus 4, -1, on -2 over x, 8 over x squared, and then take the limit as x goes to infinity, goes to 0, goes to 0, goes to 4, goes to -1, to 0, to 0. So we get -4. And from this, we conclude, based on this limit and the other limit, f has horizontal asymptote y equals 4. If they were different numbers you got in your limit, you'd have two different horizontal asymptotes, but here we have just the one. Any questions about 3 part A? Okay. So right now, I would like you to compare 3 limits we've done. 1a, 1b, and the limit as x went to positive infinity for 3a. Those results generalize. Well, those limits all took limit as x went to infinity of a polynomial over a polynomial. Those results generalize to a theorem. And I'm going to write that theorem here and talk about why it's true. Theorem. Limit as x goes to infinity. So right here in week one, we talked a little bit about general polynomials and the form they take in general. And they take the form number times x to the n plus number times x to the n minus 1 all the way down to the constant. So a polynomial of degree n has largest exponent x to the n, and there could be a coefficient on it. So what we're going to do is look at the limit of this rational function, this polynomial with degree n over this polynomial with degree m. Degree, remember, is the largest exponent in the polynomial. And we can make observations on problems 1a, 1b, and 3a, limit as x goes to infinity, and turn this into 3 cases. So I'll just include a clarification here. What this actually means is polynomial with degree n over some other polynomial with degree n. So we're taking the limit of polynomial degree n over polynomial degree m. So in particular for problem 1a, the largest exponent on top is 5. So that's degree 5 on top over degree 9. Largest exponent on the bottom is 9. And by taking a general rational function in this form, well, let's look at part A. In this piecewise equation, there are going to be 3 lines, and the first one I write will be the middle line. In part A, by an argument just like what we went over, where we divided everything by x to the 9th, if you do that in general, where you have the degree on the bottom, 9, larger than the degree on top, the same type of argument will hold, and your limit will turn into the same type of equation that turned into, where everything on top went to 0 and everything on the bottom went to some number. So if the degree on the bottom is less than the degree on the top, that limit would be 0. In part B, we had a similar situation, but part B, but degree on top was 8, degree on the bottom was 4. 8 is larger than 4, but you do the same type of argument, divide everything by x to the largest number on the bottom. It will turn into an equation like that one turned into, where we had limit of, in this case, 4x to the 4th minus 0 over some number. And in that case, as x goes to infinity, the whole function will go to, well, it could go to positive infinity, or it could go to negative infinity. after I finish this, I'm gonna write something else under here that you can compare. But if in part B, it said negative 4x to the 8, it would be a negative infinity. But if the degree on top is larger than the degree on the bottom, it would turn into something like part B turned into, where we got a limit of positive or negative infinity. Now, we have this case, degree on top less, this case, degree on top larger. Well, what happens if they're equal? Well, if they're equal, you can look at our work for part 3A. Our work for part 3A, notice toward the end of the limit as x went to infinity, the negative 4 on top and the 1 on the bottom were still there. And they turned into, well, their ratio turned into our limit. So this limit, if the degree on top is the same as the degree on the bottom as it is in 3A, the limit would be given by the ratio of their coefficients on the largest exponented term. So, and I'm never going to ask you to state this theorem. I'm never going to ask you to even explain this theorem. But this theorem could serve as a shortcut for some of these limits we've done. Now, on the first test, odds are I will ask you to not use the theorem, but as we go through the semester, there will be times when we make this an observation, largely the first observation. So I'll just say, for now, compare these three cases to 1A, 1B, 1A, 1B, and 3A, the limit as x went to infinity. This is, it is an important result in math. It's an algebraic result. With this, you wouldn't necessarily have to go through a lot of the writing we went through, but a lot of the writing we went through is turning it into calculus observations, which is important. So I will never say, use this theorem, state this theorem, tell me what it means. But it is useful to compare these to those three questions, because these types of limits do generalize to a pretty nice theorem. I'll also add for the positive negative infinity if negative 4x to the 8, and it's positive infinity because it was positive 4x to the 8. Any questions about that? Okay, this is in the textbook. I think it's in chapter 4, section 6, I believe. Notice that theorem didn't say anything about limits to negative infinity. Many limits as x goes to negative infinity will turn out the same as x goes to positive infinity. Some won't. We saw in lecture a question, I believe it was the second to last one we did. We saw a question where we got different answers as x went to positive infinity versus negative infinity. So here we have this function. We need vertical and horizontal asymptotes. Well, again, for vertical asymptotes, we'll set the bottom equal to 0 and see what we get. Well, what happens here? Does this factor? It does factor. Why does it factor? Well, I set it up to factor. How does it factor? Well, we need to make a positive 2 and a negative 7. If we do this, well, that's not going to work because it makes a positive 2, but it makes negative 2 minus 3, negative 5. And negative 5 is not negative 7. But if we do this, oh, that's what I did. If we do this, well, these multiplied give a negative 2, and the middle term would then be negative 6x minus x, making 7x. And now we just set each of these equal to 0. Add 1, divide by 3. Add 2. So you get x equals 1/3 and x equals 2 as our vertical asymptotes. Any questions about the vertical asymptotes here? So now we have horizontal asymptotes, and we're going to do the same type of argument. Notice that a coefficient argument didn't have any square roots in it. It could be extended to square roots, and we'll see. I'll mention that once I get to this answer. But the largest exponent on the bottom is 2. We have 1 over x squared. And what does this turn into? Well, in the bottom, what do we get? We get 3 minus 7 over x plus 2 over x squared. What do we get on the top? Well, we have a square root on the top. We can't just throw this x squared into the square root. If we want to multiply this into the square root, we need a square root on this term. Well, how can we write x squared with a square root? Well, we can do it like this. X squared is the square root of x to the 4th. So we rewrite x squared as the square root of x to the 4th, and that allows us to bring that x to the 4th inside. 4x to the 4th divided by x to the 4th is just 4. -1 divided by x to the 4th is -1 over x to the 4th. And I guess I'm going to go up here now. And now we can take this limit piece by piece. 4 doesn't change, that goes to 0. 3 doesn't change, that goes to 0, that goes to 0. So we get root 4 over 3, which is 2/3. Any questions about this limit? So we needed to get this under the square root. So we threw a square root on that. We couldn't change the x. We couldn't change that it was an x squared, so we made it the square root of x to the 4th. And notice square root of 4 and 3 kind of do look like the coefficients on the largest exponent of terms. But now we need the limit as x goes to -infinity. And to do that, for this one, this argument actually does work. I'm not going to do that, because with the square root, there's technically an additional observation you have to make here, which makes this one positive. So in the lecture, we had one with a square root that did give us a different limit for -infinity. This one doesn't. I guess I'll just tell you now. The reason for that is those are even exponents. But because with a square root, we could potentially get a different answer as x goes to infinity versus -infinity. I like to convert it into a limit as x goes to +infinity by changing all x's with negative x's. -x to the 4th is x to the 4th. In the bottom, -x squared is x squared. +7 or -7 times -x is +7x. And then we have +2. And now limit to +infinity, we again use our largest exponent on the bottom argument. And here we observe we do need a square root again. And this turns into this limit. Which does look quite similar to the last one, except on this term, but that term again goes to 0. So here, this limit would be 2/3. So it is worth comparing the work we did for this one to the work we did for the one in the lecture where we got different answer for x going to negative infinity, to see where the negative shows up. And it is because the negative doesn't show up here because we have even exponents. So here we have one horizontal asymptote, y equals 2/3. Any questions about that? Okay. So I'm going to write this one up here. So this last one is a quick question. We will be done in about 1 minute. What time? My computer says 3:14. So that's okay. If you do have to go, the answer to this is 4/5. So here we have a piecewise function. We want to know what value for x, or no, what value for a will make this continuous. Well, and then it says, why does this make it continuous everywhere? Well, let's observe these functions. These two functions, remember, continuous just means, it means you can draw it like that, in one piece. So right here, what we have is a function where before 5, it's some line. And then after 5, it's a parabola. But this value of a will tell us we can move this line so that these 2 points intersect. And we can describe that using the limits. And what we need here is for the limit on the right to equal the limit on the left. So let's set up those limits. Limit x approaches 5 from the left, while on the left, the function is defined as that line, 7ax minus 3. And what do we get as x approaches 5? Well, algebraic limit laws let x equal 5. 35a minus 3. And we're going to want that to equal what happens on the right of 5. So let's find what happens on the right of 5. On the right of 5, this function is defined as x squared. So the limit as x approaches 5 of x squared, algebraic limit laws, is 25. So we want the limit on the right to be the limit on the left. So we need an a value that makes 35a minus 3 equal to 25. Well, solve for a, add 3. 35a is 28. Divide by 35. You get a is 28/35, which reduces to 4/5. On the worksheet, it says, why does this make it continuous everywhere? We are out of time, and why does it make it continuous everywhere? Well, this is continuous, that's continuous, and now they equal each other at 5. I've never asked one like that, but any questions about this one or anything we covered on this worksheet? So there is no homework, no written homework over the weekend, but it would be a good idea to consider that theorem we wrote and compare it to the problems from the worksheet. It's forcing yourself to see that is quality mathematical thinking. And that's a good thing. And if you're not going to be working on problems, that's a good thing to consider doing. But there is no homework for the weekend, no written homework. You can keep in mind we have a test week 5, or no, week 6. Sorry. So we have 2 more weeks of class and then a test. So it might be worth your time to think about how you might start preparing for that. But I do hope you have a good Thursday and a good weekend. And Thank you for showing up. That's a little late, but thank you for showing up.
Thank you.
Thank you.
Thank you.
Mhm.